Hey guys, in this video we'll talk about section 4.1, divisibility. If you haven't started your reading assignment, I would recommend that you at least read through section 4.1 before beginning this video. That way some of these terms that I use will be more familiar to you. So let's get started with talking about divisibility. The division algorithm is used to write how a dividend and a divisor are related to each other. So what I have here in the red box, A equals B times Q plus R. This is essentially the division algorithm where B is called the divisor, A is the dividend, Q is the quotient, and R is the remainder. So sometimes it's better to write this in terms of words. That would say something like our dividend is equal to our divisor times our quotient plus whatever remainder we might have. In the special case when we do division and the remainder is 0, we say that B divides A. In other words, our divisor divides the dividend, and we use this shorthand notation B vertical bar A. So B vertical bar A is read as B divides A. If we look at a couple of examples here, we can say, well, we can ask the question, is 27 divisible by 5? Meaning, can we rewrite our dividend, which is 27, as a product of our divisor and a quotient? So can we write 27 equals 5 times some quotient plus a remainder of 0? Maybe we recall that 5 times 5 times 5 is 25. So we can say 5 times 5, that's 25, but then we would need to add in a remainder to get to 27, so it would be a 2. In this case, because our remainder is not 0, we would say 5 does not divide 27. What about 42 divided by 7? If we treat that as a division algorithm problem, we would write our dividend, 42, is equal to our divisor, 7, times some quotient plus hopefully a 0 remainder. And maybe you remember that 6 times 7 is 42, which means our remainder would be 0 here. Therefore, yeah, we can say that 7 divides 42. So in this section, we're going to look at a series of examples of division questions. And the thing that we're asking is, does one number divide another number? Meaning when you do the division, do you get a 0 remainder or not? If you do get a 0 remainder, then we say yes, it does divide. If you get a non-zero remainder, we would say no, it does not divide. So let's check a couple of examples here. 3 divides 12. We want to answer this as a true or false question. So we're going to try to write this using the division algorithm. And I'll write that at the top so we can remember. It says dividend needs to be equal to our divisor times a quotient plus a remainder. So when we have something like 3 divides 12, we can identify 3 as the divisor and 12 as the dividend. And we can attempt to write that using the division algorithm and find out what the remainder would be. So 12 would be equal to 3 times some quotient plus a remainder. 3 times 4 is equal to 12. So in this case, we would have a 0 remainder, and we would say that this is a true statement. Moving on to our next problem, we're asking the question, does 0 divide 2? 0 is our divisor, 2 is our dividend. So when we write this using the division algorithm, we would have something like 2 equals 0 times some quotient plus a remainder. Well, when we try to find a quotient that makes this a true statement, notice that any number we put inside of the parentheses, when we multiply, we'll get 0. So it doesn't matter what number you put in for the quotient, that product would be 0, which means we would have to have 2 in our remainder spot in order for this to be a true statement. And since the remainder is not 0, we would say this is a false statement. Moving on to our next example, we see 0 is even. We want to classify that as a true or false statement. We know that all even numbers are divisible by 2. So we're going to check to see, is it true that 2 divides 0? If it is true, then we should be able to write 0 is equal to 2 times some quotient plus a 0 remainder. The only number that would work inside of this parentheses would be 0. 2 times 0 is equal to 0. 0 plus 0 is still equal to 0. And that's a true statement. 0 is definitely equal to 0. So we know that 0 is in fact an even number because it's divisible by 2. Let's look at our last statement here. Notice that our division symbol is slightly different than it was in the previous examples. This division symbol has a diagonal slash through it. That's basically saying does not divide. So we're asking if that's true. Is it true that 8 does not divide 2? In order to determine if that's true, we'll try and write this using the division algorithm. So 2 should be equal to 8 times some quotient plus our remainder. Well, if I multiply 8 by anything, any whole number, I'm going to get something that's too big. So I would have to plug 0 in for our quotient. That would say 2 equals 0 plus whatever our remainder needs to be. And in that case, our remainder would have to be 2 to make this a true statement, saying 2 equals 2. Since we did not get a 0 remainder, we know that it's true 8 does not divide 2. Looking at these types of divisibility questions, one thing that I see a lot is being confused by which is the divisor and which is the dividend. In this notation, the first number, the number on the left side of the vertical bar, that's our divisor. The second number, the one on the right of the vertical bar, that's our dividend. And so if you stick to our division algorithm, you can plug in the dividend and the divisor, find a quotient that gets you close to your dividend, and then add whatever remainder you would need in order to keep that equal sign true. If the remainder is 0, then it's true, the divisibility is true. If the remainder is not 0, then you would say does not divide, so the divisibility is false. Let's try some more here. So for all whole numbers a, so we're going to let a just represent any whole number you could imagine, like 1, 2, 3, etc. And here we want to check, is it true that 1 divides a? So 1 is our divisor, a is our dividend. We'd write something like a equals 1 times a quotient plus a remainder. So we need to pick a number to plug in for our quotient, and we need to pick a number to plug in for our remainder. If I want 1 times something to be a, I would just multiply 1 times a. And in that case, the remainder could be 0, and this would still give us a true statement. A is equal to 1 times a plus 0, or a is equal to a. So this would be true. Looking at our next example, for all non-zero whole numbers a squared divides a to the 5th. So again, we'll try and write that using our division algorithm. We'd write our dividend, a to the 5th, equals our divisor, a squared, times some quotient, plus a remainder. If we remember our product of same base with different exponent rules, we know that in order to turn a squared into a to the 5th, we just need to multiply by a to the 3rd. And in this case, again, the remainder could be 0. So we would have a statement like a to the 5th is equal to a squared times a cubed plus 0. And that does, in fact, simplify to a to the 5th equals a to the 5th. So another true statement. Next example, we have 3 divides 6 times n for all integers n. Integers, those are positive and negatives. So let's remind ourselves what an integer is. That's the set of all the negative numbers and all the positive whole numbers. So we're asking, is it true that 6n can be written as 3 times some quotient plus a remainder? In order to make this statement true, I need to plug something in for my quotient that when I multiply it by 3, it looks like 6n. So let's try 2n with a 0 remainder. 3 times 2 is 6, but that's multiplied by n, so we have 6n plus 0, and that's another true statement. 6n is equal to 6n. So it is true that 3 divides 6 times any integer. Moving on to our next example. This one says 3 does not divide the product 5 times 7 plus 9, 5 times 7 times 9 times 11 plus 1. So in order to define this as a true or false statement, we're still going to write this using our division algorithm. So our dividend is the product 5 times 7 times 9 times 11 plus 1. And we want to write that as 3 times some quotient plus a remainder. Looking at our dividend, I notice that we have a factor of 9 showing up inside of our dividend right here. And I know 9 is the same thing as 3 times 3. So maybe what we'll do is rewrite our dividend as our quotient inside of these parentheses. And we'll have 5 times 7 times not 9, because we have a factor of 3 right here, so we'll put the other factor of 3 here, times 11. And that's almost our dividend, but we need the plus 1, which means that would have to be our remainder. And since this remainder is non-zero, we would say 3 does not divide that number, which is exactly what the original statement says. Therefore, this is a true statement. It is true that 3 does not divide 5 times 7 times 9 times 11 plus 1, because when we do that division, we would see a remainder of 1. We have one more example on this slide, and that is 0 divides 0, which means we should be able to write 0 is equal to 0 times some quotient plus a remainder. And if we can find a number to plug into these parentheses so that we can plug a 0 in for our remainder, then we should be able to write that this is a true statement. In fact, you can plug any number in here. When you multiply by 0, you get 0, and then you can add your 0 remainder. So you might say, yeah, this does divide. Unfortunately, however, because this number that we've written down inside of our parentheses is not unique, it fails the division algorithm test. So you would have to find exactly one number that works as your quotient so that the remainder is 0. In this case, we found every single number would work as our quotient, and the remainder could still be 0. So this one's actually false. It's a little tricky case. There's some properties of division that we can talk about. For example, if we know that D, some number D, divides the number A, and we also know that that same number D divides the number B, then we get for free this fact that D divides the sum of that A and B. For example, we might remember that 3 divides 15, and we know that 3 also divides 18. So because this is true and this is true, we get for free that 3 also divides the sum of 15 plus 18. And if you add 15 and 18 together, you'll see that that's 33. Maybe we recall that 33 is equal to 3 times 11 with no remainder. Therefore, 33 is divisible by 3. In other words, 3 divides 33. If we wanted to show this in a more general way, we wouldn't use exact numbers like 3, 15, and 18. Instead, we'd use letters, and we'd prove this in a general sense. So let's take that for a ride. If D does divide A, then we know that A is equal to D times some number. And we can call that number N. If we also know that D divides B, then we know that B is equal to D times some number. We can call that M. And since these two divisibility facts are true, we know that there's a 0 remainder, so we're not going to write down plus 0. If A is equal to D times N and B is equal to D times M, then A plus B looks like D times N plus D times M. These have a common factor of D in them. We can factor that out and write that as D times N plus M. And in this case, it's much easier to see D does in fact divide A plus B, because D does in fact divide N plus M. We can see that with the division algorithm. D times N plus M is equal to D times some quotient plus a 0 remainder. If we wanted the left and right hand side of our equal signs to match, we would just need to plug in N plus M as our quotient in the parentheses. For this next example, we are told that D divides A, and oops, we already did this one, just kidding. In this next example, we're told D divides A, and we're also told D does not divide B. So this would be a case like 3 divides 15, sure, no problem, but also 3 does not divide 16. So in this case, we know that the first statement, 3 does divide 15, and we know in the second statement, 3 does not divide 16. From that, we can conclude that 3 will not divide 15 plus 16. If we add 15 and 16 together, we get 31, and we know 3 does not divide 31. We can prove this in a more general sense, where we would have the second statement, the not divide statement, B would have to be equal to D times N plus some non-zero remainder. And that would carry through to show us that the sum A plus B would also have a non-zero remainder. So let's say B equals D times N plus R. And from our first statement, we can conclude that A equals D times M, for example. So then A plus B would look like dm plus dn plus r. When we try to factor these like we did on the last one, we can pull a d off of the first two terms, but we would still have the plus r. And remember, that's a non-zero remainder. Therefore, we know that we are not going to be able to divide a plus b by d, which is why we have the does not divide symbol here. In our next example, we see D divides A and D divides B. And if A is greater than B, then D will divide the difference between the two of them. So let's rewrite D divides A as something like A equals dn, and D divides B as something like B equals dm. Again, we have a zero remainder on each of these statements because D divides each one of these. So if we wrote something like A minus B, we could write dn minus dm, factor out the common factor D, and we would be able to see that D will in fact divide A minus B, because that's the same thing as asking if D divides D times n minus m, and we can write D times n minus m is equal to D times some quotient plus a zero remainder. The quotient we would need to pick is n minus m. In this next example, we are told D does not divide A. We're also told D does divide B. This is really similar to the last example, so we're not going to work all the way through it, but I encourage you to try it on your own. If we know these two facts, D does not divide A, but D does divide B, then we can conclude that D will not divide the difference between the two of them. You're probably wondering, why is this useful? And one of the examples that we have here is that it's easy to check if a large number is divisible just by looking at the separate portions of it. For example, 1,734. If we're asking, is that number divisible by 17? Well, maybe the first thing we notice is that 1,734 actually looks like 1,700 plus 34. So we're really asking, does 17 divide the sum of those things? And in the last couple examples that we did, we learned that if we can conclude 17 divides 1700 and that 17 divides 34, then we can conclude that 17 will divide the sum of 1700 and 34. Well, let's look at each one individually. 17 goes into 1700, so that would look like 1700 equals 17 times some quotient, hopefully plus a 0 remainder. And absolutely we can pick a quotient of 100, so it is true that 17 does divide 1700. Looking at our second division statement, we're asking, can we write 34 as a product of 17 and some quotient with a 0 remainder? And if you pick a quotient of 2, 17 times 2 is 34, so it's true that 17 divides that number as well. So we know 17 divides 1700, 17 divides 34, therefore we can conclude it's true that 17 will divide 1734. So we can use this technique to break down larger numbers and answer quick questions about whether or not it's divisible or it is not. Now we're going to move on to talk about some divisibility tests. And these are pretty cool shortcut rules that can help you figure out if a number is divisible by another number quickly without actually computing the division. These first 3 tests are basically done by inspection. So divisibility by 2. If we want to know if a number is divisible by 2, the only thing we need to do is look at the units digit and check to see if it's a 0, 2, 4, 6, or 8. So it doesn't matter what number I've written down, except for the very last units digit. If it's a 2, 4, 6, or 8, then we know that it's divisible by 2. So any number you make up, if you put the last digit as a 0, a 2, a 4, a 6, or an 8, then immediately you'll know that that number would be divisible by 2. Whereas if I just change that last digit by one single value, if my units digit instead were a 1, I would say this is not divisible by 2. So 2 does not divide 137,551. However, 2 does divide 1,037,552. And it's all about the units digit. The divisibility test for 5 is pretty similar. The number needs to end in a 0 or 5. If you remember counting by 5s, 5, 10, 15, 20, 25, 30, all of those numbers end in a 0 or 5. So if you make up a number and the last digit is a 0 or a 5, then you know that 5 will divide that number. But if you make up a number where the last digit is not a 0 or a 5, then you would say 5 does not divide that number. Our last divisibility test on this slide is to determine if a number is divisible by 10. Again, this is by inspection. So a number is divisible by 10 if and only if the units digit is 0. So if you make up a number and it ends in 0, then you know 10 will in fact divide that number. But if you make up a number that is not ending in a 0, then 10 will not divide that number. So these are our first 3 divisibility tests. We might have already been familiar with them before this section, but we can just formalize them using these shortcuts. Let's move on to our next divisibility test. This is for determining if a number is divisible by 4. So if we make up a number and we want to check if it's divisible by 4, all we need to do is check the number formed by the tens and the unit digit. So in this case, the tens and the unit digit makes up the number 48. So if it's true that 4 divides 48, then we can conclude that 4 also divides that larger number, 137,548. So if we can confirm that this is true, then we get for free that the second statement is true. So we check. Can we write 48 as a product of 4 times a quotient plus a 0 remainder? And the answer is yes, 12. Since we know that 4 does divide 48, we can also conclude 4 divides our larger number. Divisibility rule for 8 is very similar to the divisibility rule for 4. See if a number is divisible by 8, really similar to the divisibility test for 4, but this time we're going to look at the hundreds, tens, and unit digits to see if that number is divisible by 8. So if I made up a number like 137,128, and I wanted to check to see if that's divisible by 8, all I need to do is look at the last 3 digits, which is 128, and ask, does 8 divide that number? If it does, then we get for free that 8 divides the larger number. So we go back and check. Can we rewrite 128 as a product of 8 times a quotient with a 0 remainder? The answer is yes. We would pick 16 as our quotient. 8 times 16 is 128. Therefore, 8 does divide 128, and we can conclude 8 does divide our larger number. Let's use our divisibility test to determine if the number 97,128 is divisible by 2, 4, and 8. If that number is divisible by 2, then it has to end in a 0, 2, 4, 6, or 8. It does. Our number ends in an 8, therefore 2 does divide that number. To check and see if it's divisible by 4, we need to check the last 2 digits. That makes up the number 28. If 4 divides 28, then 4 divides the larger number. 4 does divide 28, therefore 4 will divide our larger number. And then lastly, to see if our number is divisible by 8, we look at the hundreds, tens, and units place. That's the number 128. If 8 divides 128, then 8 divides the larger number. We just said 8 does divide that number, therefore we know 8 will divide the larger one. Let's try this again. We have 83,026. We want to see if this is divisible by 2, 4, and 8. Our number ends in a 6, therefore it's divisible by 2. The last 2 digits are 26, so we would need 4 to divide 26. Unfortunately, 4 does not divide 26, therefore 4 will not divide that larger number. And then checking for 8. To see if 8 does divide this number, we need to see the hundreds, tens, and units place. That makes up the number 026. If 8 divides 026, then 8 also divides our larger number, but it does not. 8 does not divide 26, leaving behind a 0 remainder, therefore 8 will not divide our larger number either. Test for 3. So this rule says the sum of the digits of the number has to be divisible by 3, and if that's the case, the original number will be divisible by 3. So let's make up a number like 12,345. We want to check, is it true that 3 divides this number? So to use this test, we're going to write the sum of all the digits. So 1 plus 2 plus 3 plus 4 plus 5. 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, 10 plus 5 is 15, so we know the sum comes out to be 15. 3 divides 15. We know that because 15 is equal to 3 times 5 with a 0 remainder. Therefore, we know 3 will divide our original number. What if instead we were looking at the number 12,344 when we add our digits together? Instead of 15, we get 14 for the sum of the digits. We know 3 does not divide 14, therefore we can conclude 3 will not divide our original number. The divisibility test for 9 is very similar. In order to determine if a number is divisible by 9, we're going to add the digits up just like we did for the test for 3, but this time we're going to check to see if that sum is divisible by 9. So if we worked with the same number, 12,345, we know the sum of those digits came out to be 15. 9 does not divide 15, therefore 9 does not divide our original number. But if we looked at a number like, if we looked at a number like 12,348, when we add those digits, 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, 10 plus 8 is 18. The sum of our digits is 18. 9 does divide 18 because 18 is 9 times 2. Therefore, we can conclude 9 does divide our original number. So these are our shortcuts for 3 and for 9. Add the sum of the digits. Check, is that sum divisible by 3? If it is, then the original number is divisible by 3. And you can also check to see if it's divisible by 9 using that same sum, but checking to see if that sum is divisible by 9. Let's use these two rules. We have the number 1002, and we want to see is that divisible by 3. So we add the digits. The sum of the digits comes out to be 3. 3 does divide 3 because 3 is equal to 3 times 1 with a 0 remainder. Therefore, 3 divides the larger number, 1002. Checking to see if it's divisible by 9, we use that same sum. This time we're going to check, does 9 divide that sum? It's easy to get this confused and to say yes it does, but remember that we're trying to write 3 is equal to 9 times a quotient plus a 0 remainder, and we don't have a whole number that will work here. Therefore, 9 does not divide 3. Although it's true that 3 divides 9, 9 does not divide 3, therefore 9 does not divide our larger number 1002. Let's check this on another number, 14,238. So if we want to check to see if that number is divisible by 3, we need to add the digits. One plus 4 is 5, 5 plus 2 is 7, 7 plus 3 is 10, 10 plus 8 is 18. 3 does divide 18, therefore 3 divides the larger number. 9 divides 18, therefore 9 also divides the larger number. So in this case, both tests passed. Divisibility test for 6. If a number is divisible by both 2 and 3, then it's also divisible by 6. So if you want to check, is the number I'm looking at divisible by 6, you're going to need to apply 2 rules. You're going to need to check if that number is divisible by 2 and if that number is divisible by 3. So if we use something like 137,462, and we want to ask, is this divisible by 6? We're going to check if it's divisible by 2, and we're going to check if it's divisible by 3. So in order for this number to be divisible by 2, it needs to end in a 0, 2, 4, 6, or 8. It does end in a 2, therefore 2 will divide our number, 137,462. And if we want to see if this number is divisible by 3, we'll add all of our digits together. Seven plus 3 makes 10. 4 and 6, that makes 10. So I have 20 plus 1 plus 2 is 23. 3 does not divide 23 because 23 is 3 times 7, which is 21, plus 2, and that's a non-zero remainder. So 3 does not divide 23, which means 3 does not divide our larger number. Although 2 passed, 3 did not. Therefore, this number is not divisible by 6. So 6 does not divide 137,462. If both of the tests had passed, then we could say that the number is divisible by 6. If we change our number just slightly, instead of ending in a 2, if we have it end in a 0, that number is still divisible by 2. And this time when we add our digits, we get 21. 3 does divide 21, therefore 3 also divides our larger number. Since both rules pass, we would say that 6 does divide 137,460. Divisibility test for 11. Now this one can sound pretty tricky, but when you take a look at it, it's not so bad. A number is divisible by 11 if, and only if, the sum of the digits in the places that are even powers of 10 minus the sum of the digits that are odd powers of 10 is divisible by 11. So let's come up with an example here. So we're looking at 1,235,321. If we remember our place values, we start off with 10 to the 0 power, that's our units place, 10 to the first, 10 to the second, 10 cubed, 10 to the fourth, 10 to the fifth, then 10 to the sixth. So I've underlined all of the numbers that have the even powers of 10. This rule says to add those up. We get 8. And then it says to add up all of the powers of all of the digits in the odd powers. So that'll be the 2, the 5, and the other 2. That'll give us 9. Then the rule says to find the difference between these two sums that we found. So we would do something like 9 minus 8. That's equal to 1. 11 does not divide 1, since 1 cannot be written as 11 times a number with a 0 remainder. Let's try another one. Let's try the number 52,635. So we'll look at the even digits, the digits that are in the even powers of 10, so that would be 5, plus 6, plus 5. And then we'll add up the odd digits. So that's the 3 and the 2. The sum of the digits in the even powers of 10 place value comes out to be 16. The sum of the digits in the odd powers of 10 place value comes out to be 5. When we do the difference, 16 minus 5, we get 11. If it's true that 11 divides that difference, then it's true that 11 divides the original number. And 11 does divide 11 because 11 is equal to 11 times 1 with a 0 remainder. Therefore, we know 11 divides our larger number. Now, so far we've worked with pretty large numbers, 6 or 7 digit numbers, but these rules will work on even larger numbers than that. 57,729,364,583. We can quickly decide if that number is divisible by all of the numbers that we've determined rules for. So we check first, is this number divisible by 2? Well, it ends in a 3. Numbers that end in 0, 2, 4, 6, 8, those are divisible by 2, but numbers that end in 3 are not. So we move on. Is this number divisible by 3? Well, to determine that, we need to add our digits. Adding these up, let's see, I have a 6 and a 4, that's a 10 there. I have a 7 and a 3, that's another 10 there. I have a 7 and another 3 over here, that's another 10 there. I have an 8 and a 2, that'll make another 10 there. So I've used this number, 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 and this number to get 40. Plus I still need to add this 5 and this 5 to get 50. So we're asking, does 3 divide the sum of the digits? Does 3 divide 50? No, it does not, because 50 would be 3 times 16 plus 2. Non-zero remainder, therefore 3 does not divide 50, therefore 3 does not divide our larger number. Moving on to our next rule. Actually, before we move on to our next rule, remember that the test for the divisibility for 9 is going to depend on this same sum. So let's go ahead and check and see if this number is divisible by 9 since we've already added up all of the digits. So we need to know, does 9 divide 50? Well, 50 would be equal to 9 times 5. 9 times 5 is 45, which means we would need to add a remainder of 5 since that is not 0. We know 9 does not divide 50, so we can rule that one out. Let's do the divisibility test for 5 next. If this number is divisible by 5, then it needs to end in a 5 or a 0. Our number ends in a 3, therefore not divisible by 5. Let's also do the divisibility test for 10. Our number would have to end in a 0 to be divisible by 10. It does not, therefore our number is not divisible by 10. We can check the divisibility for 6. In order for this number to be divisible by 6, it would have had to pass the divisibility test for 2 and for 3. Remember, it did not, therefore not divisible by 6 either. The only ones we have left are 8 and 11 to test. Remember that for the divisibility test of 8, we need to check if 8 divides the 3 digits made up from the hundreds, tens, and ones place values. So does 8 divide 583? We can use short division to check that. 8 goes into 8 once with no remainder. 8 goes into 5 0 times. Eight goes into 53 6 times. But 8 times 6 is 48, which means we have a remainder 49, 50, 51, 52, 53 with a remainder of 5. Therefore, 8 does not divide 583, and ruling out 8 as a divisor of our 57 billion number. So the only possible divisor that we have left that could pass might be the 11. So let's take a second to try that. Checking to see if this number is divisible by 11, we know we need to add the digits in the evens place powers of 10, and then we need to add the digits in the odd powers of 10, and then find the difference. So even place, we have 3, 5, 6, 9, 7, 5. We need to add those digits together. Adding these up, I see 5 and 5 is a 10. 7 and 3 is another 10. 9 and 6 is 15. So this is going to look like 35. Now adding up the other digits, so all the digits that were in the odd powers of 10 place, we have 7 plus 2 plus 3 plus 4 plus 8. 7 and 3 is 10. 2 and 8 is 10. And then plus a 4, we have 24. So finally, we just need to find the difference between these numbers, 35 minus 24. 35 minus 24 is 11. 11 does divide 11, therefore 11 does divide the number 57,729,364,583.